Good morning, welcome. We're going to finish chapter 29 on weighted graphs today. Next week is the Thanksgiving week, and after the Thanksgiving week, we will have a review for the final exam. All right, so let's get to the last section of chapter 29. We're going to give an application using a weighted graph to solve a problem. So this is the problem. We already know this problem. So let's go to the problem. We have introduced it in the preceding chapter, in chapter 28. So we introduced this problem, the 9 tails problem. So in this 9 tails problem, we attempt to find the minimum number of flips to flip the 9 coins. Each coin has 2 faces, a head and tail. So you can only flip the head. When you flip the head, you also flip its neighboring cells. So here, for example, we have this pattern. We flip this right here. We're going to flip its neighboring. So this is the one. This is the 3 here. H, T, H. They're going to be also flipped. So this flipped. All right. So now we're going to flip one more time right here, and everybody is now a tail. So this is the solution, and we have 2 flips. All right, we're going to have this variation of this problem, and to count. Actually, when you so here's the pattern. When you flip this H right here, so that's 1 flip, and also when you this adjacent cells, and they are also flipped, they're also counted. So the total, if you flip on this edge, so you are actually count this as 3. All right, so if you flip on this edge, you count it as 4. So this 4. So now if you flip on this edge, and you're gonna count as 4 here, and you flip on this edge, you're gonna count as 5. So here is 5. So we're gonna assign a weight. So the objective is we need to find a solution that's the optimum. It's a minimum number of these counts. Okay, so it's minimum number of flips, but you count each flip, you have a weight on each flip. All right, so now, and we're gonna have this is becoming a weighted graph problem. So, and we're gonna model the thing as before. So this is the all the patterns. So we have 9 cells, and so we can build a graph for 512 vertices. So this is 512 vertices, and we can just label the vertices using the number. So this is very interesting here. You can simplify it. You just call it 0, 1, 2, 3, and this is 511. Now from the numbers, you can generate the pattern. So here is 0, so you have all zeros here in the pattern. And here is 511. You have all ones in the pattern. And this one here is a 3. So you have this is 0, 0, 0, 0, 0, 0, and 0, 1, 1 as the pattern. So it's very easy. And the unique correspondence. And you have a number. And you can generate a pattern. So you don't need to store the pattern in the program. And because this can be generated. All right, so make things really easy. All right, so we have all this. And how do you create the edges? So remember, we create the edges as this. This is the one here, and so you for instance, and here is 56. So 56 is this pattern 0, 0, 0, 1, 1, 1, 0, 0, 0. So this is the number representing 56, and likewise, and 56 generates this pattern. Any questions? Any questions? All right, so now there's edge. So here's the edge. All right, so if you flip here, so this is 0, you flip the 0 and flip it. So this becomes 1, and it's adjacent, and this is the sales. And so this 0 becomes 1, and this 1 becomes 0. So it becomes, this is the pattern now. And this pattern, corresponds to number, it's 408. So here there's from vertex, and this is the 408, a label 408, and to vertex 57, there is a direct edge. So that's the edge. So now if you can flip it, and there's an edge here. So now look here, you have everywhere you have a 0, so there's a potential edge. So you flip it, and that's going to be leading to some other vertex coming to this. So that's, for example, here, we're going to flip on this, this 0 right here for 488. We're going to flip on this 0. So this becomes 1, and now it's adjacent cells. And so this is 0 is all becoming 1. So now it comes to this 511. So there's an edge from 511 to 488. All right, so this is the, we're gonna now, we have the same graph, but we're gonna assign the weight on the edge. So from here, 56, so this is here, you flip on this one, the first one, the upper left, 0, and becoming 1. So you actually, this is 3 cells affected. So this is the one, it's adjacent, this is 0, and this is 1. So this is right here. So the weight on this edge is 3. All right, so here, from here, this one right here, 488 to 511. So you flip down this right here, this one, and the number of actual flips is 4. So that is the weight on the edge. All right, so that's the one. See, the same as before. You build this exactly the same thing as before. And now you can apply create a weighted graph and apply the breadth first search. Not so. This is the one here when we did breadth first search, and we don't consider the weights. But now you have the weights. You find the shortest path from the root and to any of the vertex. You have to use the shortest path algorithm. All right. So I'm going to go with duplicate the tab. I'm going to open another tab here. And open this tab. And here is the weighted 9-tails problem. And this is here. All right, so here, we have the weights now, okay? And so what we're gonna do is this. We're gonna have this model. So previously in chapter 28, we have this model is for 9-tail model. It's unweighted. Okay, so in that model, we create unweighted graph. Okay, so this is the unweighted graph we created. And so we create an unweighted graph, and then we get the tree, and that's using the breadth first search. That's the tree here, right? The tree. So look here, the pound sign here, when we design it, so this means it's protected, okay? All right, so here for the subclass, we're gonna have this subclass to override this tree, okay? So this here, it's weighted 9-tail model. It's a subtype of 9-tail model. So look at the tree here. We're gonna change this tree to the shortest path tree. It's a search tree, so it's a subtype. So this tree is going to be changed. And if you go to the weighted graph, for the shortest path tree, so we're going to have that tree. For the tree here. So here, we're going to inherit all this, okay? And from the 9-tail model and to weighted 9-tail model. So this is to create a weighted 9-tail model. All right, so for how do you create a weighted 9-tail model? So you have to build, this is the weighted 9-tail model. So here is extends 9-tail model. All right, and so we're gonna get the edges. So when we get the edges now, this time we're gonna have a width. So in addition to all this relationship, the edge relationship in the unweighted graph for 9-tail model. So now we also add this width here. This width is a number of flips here, number of flips for each. So when you have the edge, you also need to get this number of flips. So you're gonna flip the node and get the flipped node. You flip on this cell and get that. This is the get flipped node. So get flipped node is, we already have this get flipped node. It's in this. Here's a get flipped node. Look at the get flipped node in 9-tail model. We already have this. So this one is this. Here is when you do a flip here. So here, and you flip on this here, on this 0 right here, on the bottom middle 0. So this will get the flipped one, the result, it's 511. So that's the one will get you 511. So that's the one here, get flipped node. Okay, so get the flipped node, and so that's the V. So we're gonna get number of flips from this U to V. So how many are this? So that's the number, and that is becoming the weight. So this is from U to V. All right, so this is the this one here. It's just be careful here when you have the direction. So it's from here to here. You flip it 0, the bottom middle one. So it's from here to here, but the edge is actually reversed. It's from 511 to 488. So when you flip it, it's from 488 and get this 511. But when you build a graph the other way, the reason is when we build a graph, we need to use this 511 as the root. So from this root here, and this is the one, when we do a search, we're going to start from 511 to find the shortest path. So that is, you're going to have this is the reversed way, the edge, the direction. So you can see that here is U, V. U is the V is the flipped So, and U is actually from U and to V. So that's the one. So here you're gonna see a U starting from 0 to the number of nodes, and it's 0, 1, 2, all the way to 511. So for any of this, each of one, and we look all the possible they are ahead. We're gonna flip that ahead. So this is if it's ahead, we're gonna do a flip. So that's how we construct this graph. We construct this graph, and here, we're gonna get this is we get this list of all the widths, and we're gonna return, and this is going to return the edges. So this is the edges right here, and the edges is returned edges. So this is all the edges. All right, so here we get edge, we return the edge, and we construct the graph. It's the weighted graph. So now, look at this tree is, what is tree now? So this tree is the shortest path tree from this graph. So this one is the graph here, and we're gonna get shortest path starting from 511. So that's the one, that's the pattern for all the tails. All right, so, and this is the get number of flips, and we have, and this is so is get number of flips here. It's yeah. So here we have, this is the so we have this we have get number of flips, and this is from U to V is returns the number of the different cells between the two nodes. So it's from U to V. When you flip and etch the head, and in this pattern of U, and how many actual flips you have, and in order to get this the V here. So this one here, it's it looks like it's overloaded methods. This is actually returns the number of flips from this U, the node U, to the target node 511. So that's going to be the shortest path, and from 511 into this T. So that's the one. So we have this is this weighted graph here, weighted graph, and you get the shortest path, and this is the tree here. So we're going to cast this tree into the shortest path tree. So that's just do a casting, because this is something you let's look at this is in Java, when you program in Java here. So this is tree. What is tree? Where is tree defined? It's not here. Tree is defined here in this model here. The tree is defined here. Tree is here. And it's defined as search tree. Shortest path tree is a subtype of search tree. That's fine. There's no problem. All right, so that's tree. That's a data type of tree. Okay, tree here, and the declared type is search tree. All right, so here, in order to get this is the shortest path tree, you have to do a cast. If you don't do the cast, you'll not be able to compile it. You'll not be able to compile this here, because there is no method to get cost in this tree here, because this tree is defined as just a search tree. Search tree is, it's embedded. It's coming from this actually breast first search tree. So that's from the 9-tail model. But when we here we design here, we have this tree is actually the shortest path tree. It's fine. It's a subtype of the search tree, so this is okay. But when you get this cost of the shortest path from U to the starting vertex, that's 511. So this is the casting. You have to do a casting for this. Okay. All right, so we get a casting, and we so we get the cost. So the cost is here. Okay, there's one thing here is it's about this so we get this cost. The cost is, it's actually a double value. So in the shortest path tree, and we look at the cost, returns a double value. So we cast it into int. So this is the casting right here. The casting is to cast it to int right here. Cast. So that's it. Because we get the number of flips, that's the integer. So this is the one. All right, so see how we use the existing code. So we don't have to start over everything from scratch, and we already have things we built for the nine-tail model. It's unweighted version, and we just expand it and to add the weights, so becoming weighted version. So the weighted version, and we can make it as a subtype of just nine-tail unweighted version, and we can utilize all the code already developed, so we don't have to rewrite all this code. So that's what we do when we do this object-oriented design, is to reuse the code. See, it's really essential in software development. We have different paradigms and over the years, and start from the very early on, we just have the high-level language, and we're not using any objects and classes, and we just used really simple thing. It's writing code using loops and procedures. And procedures, it's another name for methods here in corresponding to Java language, just or subroutines. So that's the early on when you develop the code in the early languages, in Fortran, in COBOL. And so all this actually used for many years, 30 years, just until about 20 years ago in the I think it's the late 90s. Okay, it's just 25 years ago, in that period of time. So this object-oriented software development started to blossom. So the reason for this is just to reuse the software. So you look here, we have creating the data structure. It's a list. Okay, you just reuse it, and you don't have to rewrite the code for all those things already done in the, it's in the system, in the API. So you just use it to create an object, array list, linked list, create stack, create queue, and create a tree, binary search tree, create an AVL tree, and create graph, and create unweighted graph. So this is the idea. You reuse the software, you have that. And when you develop your own code, it's the same thing. The object-oriented thinking is you model your system in terms of the objects, and objects are they have relationship, and they cooperating together and to perform a task. So the objects of the same kind are modeled using a class, the same one class. All right. So this class we books on the data structures. In object-oriented system, each data structure is actually an object. So all these data structures or common features you define using classes. Okay. And data structures, it's object, it's contain object. It contains data. So when you write the program, and you're going to deal with a lot of data. So this is data. It's how do you manage the data efficiently, and that's the data structures. And organize the data, and manipulate data, and process the data, efficiently. So with all this, you're going to see this is from the basic data structures, and you develop the custom data structures, and you now get into advanced data structures like this complex data structure graph. We can model it and using this object or design approach. So we can use, when you have this the graph, you have this algorithm. When you implement algorithms, you process data, you use underline, you can use different data structures, so they're all together. All right, I think I'm going to end the class. All this now, this is the end. After next week, I'm going to give you a review for the final exam. All right, any questions? All right, have a happy Thanksgiving. Goodbye.
Bye.
That's great.
All right, thanks.
Thanksgiving.